11 is a long chapter talking about other theories of bonding. So let's start off with, why do we care about this? Well, morphine is a molecular imposter. It fits under certain sites in our bodies and receptor sites, and they bind to what we call opioid receptors. And this is actually a mimic. It's actually a mimic of other receptors that we have, and specifically the alpha and beta endorphins, the endorphin molecules that you get even from other things like exercise and whatnot. And they reduce pain. So and the morphine just has a very similar shape, and that's why it's great to use as for anesthesia for surgery and whatnot. So before we get into the morphine molecules, it's the shape and it fits on the receptor sites. So let's talk about molecular shapes. And a very good theory for predicting molecular shapes is valence electron pair repulsion, sometimes called VSEPR, sometimes it's called VESPR, but really VSEPR. And much like Lewis theory, this theory is wrong. The most correct theory is molecular orbital theory, which we'll cover later in this lecture. And the real reason, I'll just go ahead and say, the real reason why things bond is that the combination of the electronic and magnetic properties of the nuclei and electrons come together. And if there's a certain organization in terms of geometry and bonding electron groups, if that is lower energy, then the bonds tend to form. And the organization of these almost exactly fits Lewis and VSEPR theory, and later on we'll talk about valence bond theory. They're very close, but the molecular orbital theory is the strongest theory. That, and it can combine with quantum mechanics, which we don't really cover in this class. But that's the real reason why things bond. And it's even more complicated than that. The math is pretty crazy. Also, the way things form, just because a bond can form doesn't mean that it will form. It also depends on the stabilization around the molecule as it's forming. So there's very, very deep layers of complexity here. But this is an intro class, and I want to inspire you to keep on studying, of course. But let's start here. And why are we teaching it? It's because it's very useful. It's still very useful. Even though the theory is fundamentally wrong, it still predicts things most of the time. And so let's go back to the theory. Valence shell electron pair repulsion. So valence, outside shell, valence shell, outside electrons, and these outside electrons repel. And that repulsion is what creates a shape. So then the name basically describes a theory. So, and it's just what I just said, that the electron groups around the central atom, how they repel to make the geometry. So you have a central atom, and then you have electron groups around the central atom, and they repel, and then shapes are formed. So let's start out with what are defined as groups. So you see this molecule here, this NO2 molecule. Then you look at the central nitrogen. The central nitrogen has three things. It has a double bonded oxygen, it has a single bonded oxygen, and a lone pair. So those are three things, three groups. And we have five basic arrangements. You can go more than that. It's 2 groups, 3 groups, 4 groups, 5 groups, 6 groups. You can go more than 6 groups, but it's very rare. It tends not to go beyond 6, just because I mean, it's hard to get so much negative charge around a central atom. That's the reason why things tend not to go past 6, although it's possible. And we have these basic arrangements, and these are modified if there's lone pairs. So we're going to go through this and go through each of the groups. So starting off with linear, and when you have a central atom and then two bonding groups, this is linear geometry. And remember, the bonding groups want to be as far away from each other as possible. And what's the only way to be as far away from each other as possible? Is to be a straight line. And three things. So you have three things now, and these are all coplanar, meaning that they're all on the same plane. And the plane is like a flat sheet of paper. And now three groups all on the same plane. They will then be 120 degrees, or if you go by radians, it's 2 pi divided by 3 radians if you prefer radians. And so these, like I said, are all coplanar, and by definition, 3 points define a plane. That's a geometry, just a fundamental postulate of geometry. And and the central atom is coplanar to the three groups as well. So the planar geometry, now let's talk about these electron pair repulsions. So this is formaldehyde, and on formaldehyde, the oxygen is going to have lone pairs. And those lone pairs are very large negatively charged groups, and what they do is they repel the hydrogens that are attached to the carbon. They push them forward, so the bond angles are slightly skewed due to that repulsion. So valence shell electron pair repulsion, VSEPR. So using balloons to describe this, and you can see with balloons in their resting states of sorts. So 2 things have linear, 3 things have planar geometry. Okay, so a central atom and a 3-atom molecule forms 2 double bonds. What is the geometry of the molecule? It's got 2 things. That's linear. So 4 things have tetrahedral geometry, and the tetrahedron, it's a specific type of solid called a platonic solid. There's only 5 of them: tetrahedron, octahedron, cube, dodecahedron, and icosahedron. So we won't talk about dodecahedrons or icosahedrons in this class. Those are higher states of symmetry. But octahedron we will, and octahedron and cube are actually the same type of geometry as far as symmetry is concerned. And tetrahedron, though, is on its own. And tetrahedron is important because the second period, so including carbon, will only go as far as 4 things bonding. And the bond angle for this idealized bond angle is 109.5 degrees. I don't know what that is in radians, but it's the ideal bond angle then for the tetrahedron. And here's a tetrahedron, and then there's the idealized 109.5 degrees. And like I said, the tetrahedron is a platonic solid where you have all regular polygons, and the tetrahedron is you have only triangles, and it's a triangle-based pyramid, but they're all the regular triangle. So look at this molecule, the cyanide molecule. What is here's the Lewis structure for hydrogen cyanide. What is this? So the central carbon atom has 2 things, so that means it's linear. So moving on, we had 2 things linear, 3 groups planar, 4 things tetrahedral. What about 5 things? This is trigonal bipyramidal. So we have, it's kind of like a planar part, so a trigonal planar part, and then above and below the plane, there's 2 pyramids, bipyramids. So showing these pictures here, the above and below, that's known as the axial, and then you have the equatorial positions. The equatorial positions, the same thing as similar geometry to the trigonal planar, and then you have the axial positions are perpendicular to that. And since another fundamental theorem if you have a plane and you have a perpendicular bisector, it is the line bisecting the plane perpendicular is perpendicular at all points along that, well, at least where it's bisecting. So the axial chlorines in this case for the phosphorus pentachloride, the axial chlorines are perpendicular, at least in bond angles, to each of the chlorines along the equator. And here shows the bipyramidal structure. And moving on to six things. Six things is octahedral geometry. And I mentioned before that an octahedron and a cube is the same symmetry. You can actually fit an octahedron in a cube and vice versa. So the symmetry is exactly the same. And the bond angles for everything in an octahedron is 90 degrees. So here shows an octahedron for sulfur hexafluoride. And you have every bond angle. Each of them are equivalent. So, I mean, you can't really say equatorial alongside here. Although if lone pairs are added, they will add not perpendicular to each other, but 180 degrees to each other. So we'll talk about that later. And here's the octahedral geometry. If you look at the center, you can draw, if you put a center in all the triangles in the octahedron, you will draw a cube. And if you have a cube and you put a point in the middle of each of the squares in a cube, you will draw an octahedron. So actually octahedron and cubes have the same geometry, and certain things grow in octahedral geometry, like pyrite, fool's gold. You can find them in cubes and octahedra. It's the same. It's the same symmetry, same growth pattern. So I mentioned this before about lone pairs. So the theory's name, VSEPR, valence shell electron pair repulsion. So the electrons where they add, they're going to cause repulsion, and they're going to change the bond angles. And why is that? Well, so a lone pair doesn't have a nucleus to draw it in. So because of that, it just spreads out. It opens up, just kind of lets itself go, lets its negative charge fly out wherever it wants, because it doesn't have that positive center to draw it in. And the other negatively charged groups are repelled by that. And the electron group repulsions vary as this part. So a lone pair to lone pair is the highest. Then a lone pair to a bonding pair is greater than that. And the least are two bonding pairs. Why is that? Well, because the bonding pairs have nuclei to draw in the electron density. So it doesn't have a very large region of negative charge. So we have the tetrahedral electronic group. If there is one lone pair, this is known as a pyramidal shape, trigonal pyramidal. So three things, pyramid. And a pyramid, if you go back to basic geometry, a trigonal pyramid is a triangular base pyramid where the base is a triangle. So a tetrahedron is a trigonal pyramidal, but a tetrahedron, every bond length is equivalent. So the pyramid, though, this trigonal pyramid, it's not the same. So although a tetrahedron is a trigonal pyramid, not all trigonal pyramids are tetrahedrons. And so in this bonding scheme where you have a lone pair, these are different. If there are two lone pairs for a tetrahedral electronic group, this is known as a bent shape. So mentioned before with the lone pairs don't have a nucleus to draw in the electron density. So here is the tetrahedral groups, or the electronic groups. So methane here has all hydrogens, all bonding groups. It has the idealized geometry. One lone pair, ammonia, and so that lone pair above it causes the bonding to shift a little bit. So in water has two lone pairs, it shifts even more. So showing here, the lone pair takes up one of the sites in the tetrahedral geometry, and then it causes those bond angles to scoot down. In water, two lone pairs causes that repulsion to scoot even more. So what is the geometry of a molecule? Has an atom of 3 bonding groups and 1 lone pair, 3 bonding groups, 1 lone pair. That's going to be pyramidal, trigonal pyramidal. So 5 electron groups. So 5 electron groups. If there's 1 lone pair, this is known as a seesaw. And the seesaw, it's like an old, at least when I was a child, when we could play this in the whatever playgrounds or the seesaw. It's like a long sort of plank with a V, and that's what it kind of looks like. And then the 2 lone pair is T-shaped, but it's an odd-shaped T. It's a really long top T. 3 things is linear, and that's to deal with where the electrons go. The electrons are added along the equatorial positions. The electrons don't add along the axial positions. So the reason being is that the repulsion. So 120 degrees is a much better repulsion. 120 degrees and 180 degrees is a much better repulsion than being in the axial, because the axial is perpendicular to everything. So it's actually further away to be in the equatorial. So that's a seesaw right there, geometry. And here's the T-shaped with 2 groups there, and you have the T-shaped. And 3 things is linear, so adding to the axial position. So with octahedral geometry, having 1 electron group, you get square planar. Square pyramidal. 1 group is square pyramidal, and even those are all equivalent. If you add 1 group, the other group's going to add to the opposite side. It's going to be as far away from the other electron group as possible, or the other lone pair. And that one's square planar. And so the definition of a pyramid, you have the base, and in this case it's a square. So the trigonal pyramidal, you have a triangle as the base of the pyramid. Now you have a square pyramid. Square pyramids like the Egyptian pyramids. So the first one here is the square pyramidal geometry. And here's square planar. So when one lone pair is added, the other one is going to add 180 degrees from the other one, so it can be as far away from the other electron group. Here's a summary of VSEPR and gives some examples of the different geometries, which I've already covered in this lecture. So this is the summary for each of these here. So imagine a molecule that has 6 electron groups confined to 2 dimensions, therefore has a hexagonal planar geometry. Which of the following groups are lone pairs and where they're located? So if it's, this kind of breaks this is not 3 dimensions, of course, but we're at 2D. But the lone pairs are going to want to be as far away from each other as possible. So it'd be 1 and 4. So summarizing it, the number of electron groups in the central atom determines the electronic geometry. And then looking at the repulsions of the different groups of those electron geometries determines the shapes of the molecules, and which we mentioned before. And we've already gone through the summary, and the bond angles can deviate from the idealized bond angles because of repulsions from that, which is always true regarding VSEPR theory. The last one here, the shape of the molecule is determined by repulsion among all electron groups on the central atom. Now let's talk about predicting molecular geometry. This is how you do it. You draw the Lewis structure, look at the electron groups around a central atom, or central atoms if there's more than one, then classify each electron group as bonding or lone pair. And it doesn't matter if it's single, double, triple bonded, it's just the bonding group. And then use a table to determine the bond angles. So also, how do you show molecules on paper? Although molecules on paper sometimes are referred to as a Fisher diagram, so you, the reader, needs to understand that the Fisher diagram is a projection. Sometimes we're written not also with this, where straight line is in the plane of the paper and then the solid wedge is moving in front of the paper coming at you and sticking into the plane and going into the paper is the hash wedge. So these are other ways to do it. So you can look here, the tetrahedral, for instance, the linear and planar, these are all coplanar. So that's not a problem. But when you start getting into the tetrahedral and the pyramids, bipyramidals, you have to, if you're using the hash and wedge, these do change the angles. So many atoms have multiple centers. So of course, I mean, if you study organic chemistry, they tend to be very big molecules in organic chemistry. So you have to look at each center and determine that for each center. So if you look at the nitrogen, it has 3 bonding groups, not listed, a lone pair. That's going to be pyramidal. Then the next carbon attached to it, there's 4 things all bonding, tetrahedral. The next carbon has 3 things. Remember, the double bonded oxygen still counts as 1. That's planar. And then the oxygen at the end of the molecule has 2 things bonding. That's bent. So including the lone pairs, then you can see probably a little bit more, especially the bent one on the end, where you have tetrahedral electronic geometry but bent molecular geometry. What is the molecular geometry about in the nitrogen and methylamine here? So the nitrogen and methylamine has 3 things bonding. It's going to have a lone pair as well. So that's going to be pyramidal. We mentioned polarity before with electronegativity and polar covalent bonds. So in this case, well, we're going to look at molecules and determine if the molecules themselves are polar, where one end is charged differently than the other end. So for hydrogen chloride, there's only 2 atoms and one is different, therefore it's going to be polar, and you have positive and negative end of the molecule. So carbon dioxide, the bonding is polar, but the oxygens are pulling equally against the electron cloud of carbon, and because of this, the 2 vectors pulling on each other cancel each other out, and because of this, carbon dioxide is nonpolar. And why do we care if things are polar or nonpolar? We'll talk about that soon. It has to do with solubility. Generally speaking, polar things mix with polar things, and nonpolar things mix with nonpolar things, and nonpolar things tend not to mix with polar things. So that's why vinegar and alcohol and water are easy to mix together, but water and gasoline doesn't mix together, but gasoline will mix with motor oil, for instance, because gasoline and motor oil are nonpolar, and water and vinegar are polar. Well, acetic acid are polar. So I mentioned vector addition before. Water, on the other hand, water is a bent molecule, and when you have the dipoles here, you have the two polar bonds. But unlike carbon dioxide, they don't cancel. Well, they cancel along one axis, but they add along the other axis. Therefore, water actually is a polar molecule. And so to determine the molecular polarity, I'll show you some pictures of the vector addition soon. So draw the Lewis structure, determine if there are polar bonds, and if there's no polar bonds, the molecule is nonpolar. So hydrocarbons, for instance, they're all nonpolar. If there are polar bonds, look at the vectors, and then combine the vectors, and see if there's an overall vector in one direction. If there is an overall vector in one direction, then that forms a polar molecule. I'll show you pictures to show you the shortcuts soon. So a molecule contains 3 identical polar bonds and trigonoplanar molecular geometry. Is the molecule polar? No, they all cancel out. So I mentioned vector addition. So example 1, these are adding together, and they have an overall vector in one direction. Example 2, they subtract, but you still have an overall movement in one direction. 3, these are equal opposite, and they cancel each other out. So now in terms of components, so you can see the top vector A and B, you have an overall vector in one direction, and same thing with this vector A and B, you have an overall they cancel each other out, and they also so they have a combination of the components cancel and they add. You have an overall vector pointing in one direction. So for 3 vector systems, you have to calculate each one individually, and then look at the overall combination of all of them. Or they can cancel out in cases, like example 7 here. So here's the summary. So determine a molecule is polar. So a couple hints. So all bents and all pyramids. If the molecule is a bent molecule or if the molecule is a pyramidal molecule, it's polar. Okay? No exceptions. So probably one of the first times you hear me say that, say no exceptions to this rule. So if it's bent or if it's a pyramid, it's always polar. Now, if it's linear, planar, or tetrahedral, so if all the bonds are identical in the linear molecule, or planar, or tetrahedral, if they're all equivalent, then the molecule is nonpolar. If one or more is different, I know there's only 2 for linear. If one or more in these bonding schemes are different, then the molecule is polar. So actually, to be nonpolar, the molecule has to have some pretty strong symmetry. Now, what about bipyramidal? So for a bipyramidal molecule, you have to look at, pretend it's a planar molecule and a linear molecule. You have to do the same rules there. So looking at the linear and the planar parts, and then determining what the symmetry is for each of those. So, and why do we care? Polar molecules are attracted to other polar molecules. And since water is polar, other polar molecules dissolve very well in water. And even some ionic compounds. Well, it says most ionic compounds. The ones that have low charges and big atoms, they'll dissolve into water. And also, some molecules, they have both polar and nonpolar parts. So we can talk about that in future chapters. Those are all sometimes referred to as surfactants as well. Soap, for instance, has a polar and nonpolar end. And other things like the phospholipid bilayer of a cell membrane, those have polar and nonpolar ends of molecules. So oil and water don't mix. Surprising you finally hear this in chemistry class. The reason is that oil is nonpolar and water is polar. That's the reason why they don't mix. And it's actually not because of the oil hates the water. Actually, oil loves water. The water is the jerk here. The problem with oil, the oil won't mix because it interrupts with the bonding scheme of water. So then because of that, water pushes the oil out of the way. And then just by gravitational field and the fact that oil is less dense, it floats to the top. So it's really the water hates the oil. Oil prefers water because it has a charge to it. But the water pushes, like I said, pushes the oil out of the way. So there's some issues with the Lewis model. It can give trends, but it doesn't give numerical predictions. And it gives good approximations for bond angles, but doesn't use the actual angle. And you can't really write the correct structure where resonance is important. So resonance only works in certain circumstances. So, and you can learn more about this in organic chemistry in higher classes. I don't want to go into it too much now, but just because a resonance structure can be there doesn't mean that it works or it is there. And also does not predict the proper magnetic properties of molecules. So oxygen, for instance, is paramagnetic, but Lewis structures would predict it to not be that fact. One of the ways we tried to overcome this was valence bond theory. And so at one point in time, valence bond theory was in direct competition to molecular orbital theory, which we'll cover later in the chapter. And they are conflicting theories. And actually, it's oxygen. Oxygen is what came about because molecular orbital theory predicts oxygen to be paramagnetic, where valence bond theory says that it should not. And because of that, valence bond theory is wrong. So here I am teaching you more wrong theories. And why am I teaching you wrong theories? Because it's still very useful. Molecular orbital theory, especially in combination with quantum mechanics, is a beautiful theory. It is very heavy in mathematics. And these other theories, Lewis theory, VSEPR, valence bond, they just make so much sense. They're using simple geometry, and we can make little models of them, and it works most of the time. So that is the reason why we're teaching you these improper theories, and these work very, very well, and it explains quite a bit of the behavior of molecules in chemistry. And as I said, the real reason is because of the fact that new orbitals are formed based off of the interactions between the electronic and magnetic fields of the electrons, mostly the electrons, and the nuclei. And if it's low energy, then it tends to bond. So that's the real reason. But let's get back into valence bond theory. And one of the things that valence bond theory comes about is the idea of hybridized orbitals. So, and this is true. This first point here is true for everything. So when two atoms approach each other, electrons in the nucleus of one atom interact with the electrons in the nucleus of the other atom. Yes, that is true. And if the energy of the system is lowered, then a chemical bond will form. This is true for everything. And then you have, but now this is where valence bond theory, this deviates. The chemical bond is the overlap of these two orbitals. And then the geometry of the overlapping orbitals determines the shape of the molecule. Okay, so those last 2 points are for valence bond theory only. And this is true. This chart here, you have energy on the y-axis, specifically potential energy. So, and then the 0 is two atoms infinitely spaced apart. So that's your 0 point. That's an asymptote. And as the atoms approach each other, the energy starts to lower. And then you get to a certain minimum point, and that is known as the bond energy in terms of the decrease in potential energy, and the distance between the two nuclei, that is known as the bond length. So that's the minimum there. And then what happens though as the nuclei approach each other? Well, then the positive nuclei start to repel, and then the potential energy goes back up, and it can get to a point where it even overcomes any bonding scheme you have. This chart is also known as the Lennard-Jones 612 potential. So you can look that up if you want to learn more about this. And with the theory, when two atoms approach each other, they start to interact and they form molecular orbitals. And these are where the electrons are shared. So this is different than molecular orbital theory, though. These molecular orbitals are different than the ones. These deal with overlap. So we'll talk about molecular orbital theory later. And let's look at hydrogen sulfide. Looking at the atomic orbitals, you would expect the bond length in hydrogen sulfide especially with the p orbitals of sulfur, you expect the hydrogens to be 90 degrees. But the bond angle is not 90 degrees. So why is it different? It has to do with the fact that it actually forms hybridized orbitals. So the hybridization, in this case, like with carbon, you have, so there's 2 electrons in the 2s orbital and 2 in the 2p's. And one of them is empty. One of the p's is empty. But these can hybridize to form we call sp3. So these will hybridize. So these are the atomic orbitals for hydrogen and carbon, respectively. But these instead are going to hybridize so hybridization, like they're in a mix, and they're going to form sp3 hybridized orbitals. And depending on the different types, and remember, so degenerate here, you see the different types. You have degenerate. Degenerate means same energy. So if you have two orbitals needed, that's sp. This is for linear geometry. sp2, this is for planar geometry. sp3 is tetrahedral geometry. sp3d is bipyramidal geometry, and sp3d2 is octahedral geometry. And so in carbon, in period 1, so hydrogen can't hybridize. Period 2, carbon is in period 2. These can sp, sp2, and sp3. And only if there's empty d electrons can there, and that's period 3 and beyond, can you go to bipyramidal octahedral geometry. So, so I mentioned before, hydrogen cannot hybridize, but the second period elements, so these can have sp, sp2, and sp3. And depending on the hybridization depends on what's going around, and I'll go over the context over where you have the hybridization under which circumstances. So carbon here, for instance, carbon has 2 electrons in the 2s and 2 in the 2p's. These can hybridize to form sp3 hybridized orbitals. And so this is the mixture of all those, and these hybridized orbitals shown on the right in purple have the different have those lobes there, and there's the positive negative lobes for the hybridization there, not shown in the picture, but then that forms the tetrahedral. All three of them form the tetrahedral bonding geometry. Now with the valence bond theory, you have the hydrogens now can overlap, and that's where the electron density hangs out, is in that overlap, and then they form the molecular orbitals that way, showing there. So this is the valence bond theory. And so nitrogen and ammonia, for instance, one of the lone pairs has an unoccupied sp3 hybridized orbital. And the interaction overlap, so the overlap, and it has to be either between the internuclear axis or perpendicular. So the internuclear axis we'll call these sigma bonds, and the parallel and perpendicular, these ones are the pi bonds. So parallel to each other and perpendicular to the internuclear interatomic. I'm using nuclear interatomic axis. I was taught using nuclear, I suppose. So how many sp3 hybrid orbitals result from the hybridization of 1s and 3 p-orbitals? That means there's 4. So sp2, you have the planar geometry here, and they combine to form the planar sp2 orbitals, all 120 degrees from each other. And that leaves one empty atomic orbital. So when you hybridize 1s and 2 p's, you leave an empty p orbital, p atomic orbital. Now the p orbitals, they can overlap. They can form either a sigma bond or a pi bond. So a sigma bond means that it fits along the internuclear axis, and a pi bond means it's above and below. So it's perpendicular. It's in the same direction of the internuclear, interatomic, I guess, is what the book is saying, but it's above and below. So if you look here at formaldehyde, for the carbon is going to have has 3 bonding groups. So that means sp2 hybridization, and has an empty p orbital. Well, has in that p orbital, well, that I should say the p atomic orbital can then interact with the oxygen. The oxygen can have a sigma bond between the carbon, so that's 1 bond, and then you have the pi bond above and below the bonding there for the between the nuclei. So sigma bond is, as I keep on mentioning, is between the internuclear axes. And the pi bond, and it's perpendicular, so above and below the axis connecting the two nuclei. And generally speaking, sigma bonds are stronger than pi bonds. Pi bonds are strong, but they're not as strong as sigma. So, and the overlap, so between a hybrid orbital, one atom with a hybridized or unhybridized orbital is a sigma bond. So, and the unhybridized p orbitals form the pi bonds. And you can have a single bond is a sigma bond, a double bond is a sigma bond and a pi bond, and a triple bond is actually a sigma bond and 2 pi. Because remember the p orbitals, there's the third one that goes, then would be coming in and out of the plane of the paper in this regards. So bond rotation, for sigma bonds, it's real easy to rotate along a sigma bond. And unless something is really, really cold, it really just moves and rotates wherever. But the pi bonds, if you twist a molecule by 90 degrees perpendicular, you have to break the pi bond. And so because of that, a pi bond really stabilizes a molecule and doesn't let it twist as much. So here shows that picture of this, and twisting the pi bond 90 degrees is going to break that pi bond. So the 1,2-dichloroethene that pi bond is not going to be easily broken. Whereas for a single bond, the 1,2-dichloroethane, it's free to rotate. It's very easy to rotate that bond. And because of that, because you have the double bonds and these are hard to break, you have the cis-trans isomerization. And we mentioned cis-trans before. And so the cis here, cis means the same side of the double bond. So the first one is cis 1,2-dichloroethene, and the other one is trans. Trans means across from each other. And these are two different molecules, and they don't easily turn into one or the other. You can get cis and trans isomerization. You can get it to shift. That's part of our photosensitivity in our eyes. Deals with cis-trans isomerization and the absorption of light, but it's hard to do. So according to valence bond theory, why is a double bond simply not twice as strong as a single bond? Because there's one sigma and one pi. And generally speaking, a sigma bond is overall stronger than a pi bond as well. So moving on to sp hybridization. So you have two sp hybridized orbitals, and then unhybridized atomic p orbitals. And for something like acetylene or ethine, so this is a linear shape, and it's going to have a sigma bond for the sp, as well as two sigma bonds. The carbon is going to have a single bond between each carbon atom, and each carbon is going to have a hydrogen, so it's two sigma bonds, and then it will form two pi bonds, at least within it's for the triple bond between the two carbons. So you have the sp orbitals, s orbital and p orbital form two sp orbitals. And then here is the bonding scheme for acetylene, where you have a sigma bond between each of the hydrogens, and each of the carbon has a sigma bond, but they have two pi bonds from the two empty p orbitals, and then they are, of course, perpendicular to each other, so as the atomic orbitals are as well. What is a hybridization of carbon and carbon dioxide? It's going to be sp, because it has two double bonds. And the double bonds are actually going to be perpendicular to each other. At least is the orientation of the pi bonds. So sp3 dehybridization, that is if you have an empty, this is only for period 3 and above in the periodic table. And this is when you can have seesaw, T-shaped, linear, well, at least for the bipyramidal electronic geometry. So here is the bonding scheme then, well, at least using the electron orbitals. You have the 3s and the 3p's, the three p's, and then one of the 3d's then forms the 5 sp3d hybridized orbitals. And then now for six things, you have the, so it's not trigonal bipyramidal, it's actually octahedral. I guess a mistake on this slide. And square pyramid and planar. These are all perpendicular to each other. And again, still has to be greater than 90 degrees. So same idea now, but you have 2Ds instead of just one for the hybridized orbitals. So here's and this goes back to VSEPR as well. So two groups, these are SP hybridized orbitals. For planar, 3 groups, sp2. For tetrahedral, 4 groups, sp3. 5 groups, bipyramidal, sp3d, and 6 groups, octahedral, sp3d2. And we can predict the hybridization, starting with the Lewis structure, use the VSEPR theory to look at the electronic geometry along the central atom, and then just look at the bonding, the number of groups to determine the hybridization. And then give the bond, the overlap. This is the valence bond theory, overlap in the appropriate orbitals, and then label the bond sigma or pi, sigma being along the internuclear axis and pi being, well, I say it above and below, perpendicular but to them, but between perpendicular but overlapping alongside the internuclear axis. So there's some limitations to valence bond theory. It predicts a lot of properties that are better than Lewis theory, but there are still some issues. It doesn't account for delocalization, for instance. So some electrons are localized and some are not. And also it doesn't fit properties as well. So specifically the magnetic behavior of oxygen. But there is a theory that does, and this is molecular orbital theory. This is just the introduction to this. So with quantum mechanics and using Schrödinger wave equation, you can go through and you can have a much more detailed discussion on molecular orbital theory. We're going to do a first approximation. We call it the LCAO approximation, linear combination of atomic orbitals. So I know this is an intro class, but this is much more complicated, and I do encourage you to learn more about this. Unfortunately, this level, the math skills tend not to be there to do that. So the equation, this is typically estimated well. It's hard to do it exactly. It's a lot of times it's computed down, and we start what the orbital should look like, but these get better with higher computer technology. And but you're not going to do this for this class, so that's for future classes. And but it explains many things, and for instance, other things like the spectroscopy of molecules. So why some things are very colorful and some things absorbed in the ultraviolet, for instance. So I already mentioned LCAO. This is the simplest part of it. And we can look at these atomic orbitals. If you remember the signs of the atomic orbitals, these can either construct or destructively interfere. So when they combine constructively, we have bonding orbitals. And when they are destructively interfered, we call anti-bonding orbitals. And then we have the electron density. We see most of the electron density is outside the nuclei, and that's true for atomic orbitals as well. But there are nodes in the nuclei, so it depends on the molecule. So looking at the 1s orbital, for instance, these can either constructively interfere to form a bonding orbital, or they can destructively interfere to form an anti-bonding orbital. And the 1s orbital is always positive. The sign on this is always positive. So, and you can see the different colors of the anti-bonding orbital. You have a change in sign. And and you can see the relative amount. The bonding orbital goes down in energy. The anti-bonding orbital goes up in energy. And this has to do with either constructive or destructive interference. It's constructive interference for a bonding orbital and destructive interference for an anti-bonding orbital. And the for and why do they form? So why would a bonding scheme form? And the answer is because it's lower energy. So if it's lower energy than the atomic orbitals themselves, and the molecule with the combined orbitals is lower energy and it forms a bond, then it'll bond that way. So problem with this is that adding electron density to anti-bonding molecular orbitals, these are destabilizing bonds. So, and it's much more complicated than this because you can add partial electron density to it. So you actually weaken bonds that way. So this tells you one of the ways you can break bonds. So, and this is important later when we talk about things like acids and bases, like how do you rip off an electron, or I'm sorry, how do you rip off a hydrogen from a water molecule? One of the ways you can do it is by adding electron density to the anti-bonding orbital, and then if that happens, then the hydrogen can fall off. So here is the hydrogen molecule, and the symmetry here is very, very strong, and this is because it's the same nucleus. So it's the same hydrogen atom is attached to another hydrogen atom equivalent, and I know we're showing here in the y-axis is the potential energy, and then the bonding orbital is down in energy, the anti-bonding orbital is higher in energy. What happens to those 1s orbitals? They go away. The atomic orbitals they disappear and they become molecular orbitals. So this is a molecular orbital. And just like atomic orbitals where you could do spectroscopy on them, we talked about spectral lines and that kind of stuff before, you can do that same type of spectroscopy using molecular orbitals. So that is one of the strong things with this theory. And I mean, and it exactly matches what we see when we do spectroscopy with molecules. You can do electronic spectroscopy using molecules. And and that's different. That's one of the differences between Lewis theory and valence bond theory and such. You don't get these numbers that you do with molecular orbital theory combined with quantum mechanics. So bond order, this is the number of bonding electrons minus the number of anti-bonding electrons divided by 2. So that is the definition of bond order. The higher the bond order, the more strongly bound a molecule is. If the bond order is 0, it's unstable. But if it's a positive bond order, that means it can happen and a bond can form. And the same idea with atomic orbitals for molecular orbitals. If all electrons are paired, it's diamagnetic, or if it's one or more is unpaired, that is known as paramagnetic, and that means it'll respond to an external magnetic field. So, and these can be fractions because it's divided by 2. And only valence electrons need to be considered for this. So this is 2 homonuclear diatomic molecules. So homo means the same. And here is 2 lithium atoms. 2 lithium atoms can come together and they actually can form a dilithium molecule. And we do see dilithium molecules in the gas phase. So this is interesting. So some of the things you learned before, lithium is a metal, it doesn't covalently bond. And now you find out that lithium does in fact covalently bond. And I love the popular, I don't know if it depends on popular, I like Star Trek. And dilithium is big on Star Trek, but dilithium is not going to be a solid. Lithium in the solid state is a metal. Dilithium can be in the vapor phase. So what about p orbitals? P orbitals can form sigma bonds. So here's the bonding and anti-bonding schemes for p orbitals. And they can also form pi bonding. And you have the bonding for the bonding scheme and then the anti-bonding scheme for the pi star, the anti-bonding orbitals. And of course there's pi bonds in 3 directions. So you can have 1 sigma and 2 pi for p orbitals. And for boron, carbon, and nitrogen, this is the first orders on the left. that the pi bond is actually lower energy than the sigma bond for the p orbitals. For oxygen, fluorine, and neon, the sigma bond for the two p's is actually lower energy. So you have an interesting switch going on here when you have that. And the reasons for this, it has to do with the electronic magnetic fields of the electrons and the interactions with them and the relative strengths of the orbitals. So this is it's very complicated, and you can learn about this in future classes. And like I said, I encourage you to continue studying chemistry and physics. Or whatever your chosen major is. It may not fit in your career pathway, but of course, I love this stuff. So, but do what is practical for yourself, of course. But I always encourage more classes. So, what is the bond order of a second period diatomic molecule containing 3 electrons in antibonding orbitals and 6 electrons in binding orbitals? So binding orbitals, 6 minus 3 antibonding, that quantity divided by 2 is 1.5. So dioxygen is paramagnetic, and to do that, I can, if you look back at the chart, I'm going to go back a few slides. So here you can do dioxygen, and oxygen has 6 valence electrons, so that means that there's 12 that it fills up. So you're going to have 2 in the sigma 2s, 2 in the sigma star 2s, 2 in the sigma 2p, 4 total in the pi 2p, and then you're going to have 2 in the pi star 2p. But remember Hund's rule, those degenerate orbitals are going to add 1 at a time. And since you add that 1 at a time to the pi star 2p, then that's going to be paramagnetic. So that's where this theory fits in. This one is paramagnetic, and in fact, liquid oxygen here does interact between a magnet, and this is what molecular orbital theory won the day, was that the Lewis theory on the valence bond theory predicts diamagnetic oxygen, whereas molecular orbital theory predicts paramagnetic oxygen. So, and this is the age of enlightenment, where we look to experimental data to verify our science, and because of that, the molecular orbital theory is correct, and then Lewis theory, valence bond theory, VSEPR is all incorrect and should be banished forever from the realms of science. And no, that's not true. It should not be banished. We still teach it because it's very, very useful, and it predicts the behavior most of the time. So although there's proper theories, or there's theories that are more proper that explain more things, it doesn't mean that these older theories are invalid. And that's the reason why we still teach it. And I still use it. I can predict using Lewis theory whether or not I'm getting an allergic reaction from drugs, for instance. So I have that ability if I know the Lewis structure. So, and we can use these theories as a simpler way to look at interactions and then make drugs. So it's they're still valuable. So oxygen described by Lewis and valence bond, it shows everything paired up. So here it would be diamagnetic. So we're going to move on to heteronuclear. So hetero means different. Heteronuclear diatomic molecules and ions, so different nuclei. And then looking at the interactions, the difference is the atomic orbitals have different energies. So homonuclear, the atomic orbitals have the same energy. Heteronuclear, they're going to have different energies. And then also that means the molecular orbital is going to be relative. So it depends on the circumstance, of course. And at this level, you don't have the math to be able to calculate that yet. So, and generally speaking, the more electronegative atom, lower energy the atomic orbitals are. So, and the low energy atomic orbitals contribute more to these bonding molecular orbitals. and the high energy contribute more to the anti-bonding molecular orbitals. And just because there's an orbital does not necessarily mean it's going to engage in bonding. So you can still have non-bonding. You can have atomic orbitals that stay around the atom. And so, for instance, here, this shows nitrogen monoxide, and you can see that the oxygen atom, the relative strengths of the potential energy of the atomic orbitals are slightly lower in energy. And then it's not as symmetric in terms of the when you saw the like the homonuclear. So heteronuclear not as symmetric, but you still have the bonding antibody. And this is still, well, it's a very reactive molecule, but it's a stable molecule. And it does, because it has a positive bond order. So this molecule will form. And but also the electron density shows it's a little more density near the oxygen, and that makes sense because it's a more electronegative atom. So polyatomic. So polyatomic means many atoms. So you can have these. So it was easier when you just have two. Now we have three or more, and we have a delocalization of electron density along an entire molecule. And these properties of using molecular orbital theory, these match the real molecule properties better than Lewis or valence bond theory. And this specifically the real molecule behavior, it's in terms of spectroscopy. So colors. So it's why the beta carotene in carrots is orange, for instance, and why the molecules in sunscreen absorb ultraviolet light. So that's kind of the explanation for this. And I know we're only glancing at the surface of this, but again, encouragement for future classes. So here is ozone, and this is the valence bond model using that, where you have a Lewis structure resonance, and then you have a valence bond. I guess you would kind of go back and forth between that with the overlaps for valence bond. But this is what you have in ozone, and you have an even split with these bonds, and it has to do with the overlap between the molecular orbitals as seen there. And what is a chemical bond according to molecular orbital theory? According to molecular orbital theory, atoms joined together or bond electrons in the atom can lower their energy by occupying molecular orbitals of the resultant molecule. So, and that is the real reason why things bond. So if you can hear it here, and I've mentioned it several times. The reason why I keep on mentioning it is it bugged me when I was a student, and I would take a class and say, oh, by the way, everything you just learned was wrong. Oh, when you learn that previous stuff, it's wrong. I'd rather start off with the truth, and still explain why I'm teaching you things that are proven false. But well, I guess not the strongest theory, I should say. Not necessarily proven false, but they're still useful. They're not universally true. And we're done. Thank you for listening.